Hello again. This is video lecture 35.2, and we're discussing in chapter 35 sections 2 and 3, in which both really we are talking about a well-known experiment in the Western tradition that demonstrated that light really does behave like a wave. Now we know to preface that statement by saying that light can, in certain circumstances, behave like a wave. And this experiment is one of those circumstances that shows very definitively that light can behave like a wave, because this experiment shows that light can exhibit interference. And interference is a wave-like phenomenon, where you take two or more waves at a given point, at a given time, and you combine them, the fancy word is superposition, to get a net wave. And the resultant amplitude of the net wave can go anything from twice the amplitude of the original waves, fully constructive interference, no amplitude at all, zero, fully destructive interference, or intermediate interference, something in between. And when this experiment was done in 1801, showing interference of light waves, then they knew it behaved like a wave, at least in this situation. The person given credit for the experiment is known as Young, last name, so it's called Young's classic double-slit experiment. And you, in fact, are doing a version of that experiment in this last lab, when you are taking a laser and shining it on a glass plate, and specifically on a two-slit arrangement in the glass plate. Then you are reproducing, under similar conditions, Young's classic double-slit experiment. So we have a number of pictures here, and it is important that we understand what these pictures are trying to show. So first, let's start on the left. What you're looking at from the side, in a very schematic representation, is a planar electromagnetic wave with wavelength lambda, traveling presumably just through air, traveling to the right, like so. And those red lines that are parallel to each other represent wave fronts, and the distance between adjacent wave fronts is the wavelength. And this planar light wave is coming upon, and we're seeing it from the side, basically a barrier, a wall, if you like. But out of that wall, a small opening has been cut. It's often called a slit. Now you're looking at this from the side, so the slit is horizontal. And it's really two-dimensional. It's got a height and a length. A height up and down, which is shown here as the distance A, and then a length going in and out of the screen that you can't see in this view. And this picture on the left is drawn under the assumption that the width or height of the slit, up and down, that distance labeled there as A, is just a little more than the wavelength of the light. In fact, it's 1.5 times the wavelength. So it's comparable. The slit width is comparable to the wavelength of the light. What happens to a light wave in such a situation? Well, it's really only that part of the wave front that lines up right there with the slit opening that's going to get through. But Huygens' principle tells me to think of that part of the wave front as a whole bunch of little point sources of secondary wavelets that will produce spherical waves going outward from there. And so the net effect is the electromagnetic wave, the light wave, propagates onward to the right, at least the part that can get through, but in going through that narrow slit, it kind of bends, flares, and gets curvature to it. So now the wave fronts have curvature as a result of going through that narrow slit. and then those wavefronts are traveling outward in all directions, like so. And that bending of the light wave, because of the narrow slit, or that flaring of it, is a phenomenon known in physics as diffraction. And that turns out to be important. If light comes across any kind of a barrier, and the size of that barrier is roughly comparable to the wavelength of the light, you're going to see a diffraction effect, this bending. All right, now that's just kind of a side point. Now let's talk about the classic double slit experiment situation. Remember, this was done first in 1801, long before there were lasers, just to be clear, right? Long before there were lasers. So what did Young do in this experiment in order to demonstrate interference of light? Okay, he had a monochromatic light source, so that could be done. He had a source that produced light that was pretty much a single wavelength, lambda. And he first sent it upon a barrier, A, that had a small slit, roughly there, S0. And he had a plane wave coming in, and it's a very narrow slit S0, so you get a good diffraction effect, the flaring of the light waves outward. So now there are the new wave fronts. They're more spherical in cross-section. And then he had another barrier, B, that had two parallel narrow slits, S1 and S2. You're looking at them again, you're looking at this whole structure from the side. So the slits just look like little gaps, but they do have a length going in and out of the screen. But they're parallel to each other and they're stacked vertically in this setup. And there's some distance between the center to center this way, which I'm going to call little d. Now, one of these wave fronts that went through S0 and has been diffracted and is now going to impinge upon S1 and S2. And that one wavelength is going to impinge upon them both. And then each one of those is going to act like a source of spherical wavelets going outward over here. So we have these spherical wavelets from S2 and these spherical wavelets that have diffracted through S1. And so now, at all points over here, to the right of those two slits, we have two light waves propagating outward. Two. And so, if you pick any point whatsoever in space and put a screen there, like maybe right there, and put a screen there, you got to put something so the light can hit it, and then you can see that, you will expect to see, if indeed light is a wave, interference. Meaning, depending upon where this point P is, you could get fully constructive interference, where the two waves are lined up and you get a big amplitude. The light will then be bright. Fully destructive interference, where the waves are lined up crest to trough and you get no amplitude and it will be dark. Or something in between, intermediate interference. And so what was discovered on the viewing screen, C, over here, parallel to the other screens, A and B, was alternating bright and dark regions on the screen, which we now call fringes. And they're called maxima if it's bright, and minima if it's dark. And this drawing shows where the maxima roughly would be, where you would see bright fringes of light, but alternating in between with dark fringes. So alternating bright, dark, bright, dark, bright, dark. That's called an interference pattern. If you did part B of the last experiment already in lab, you saw that with the laser light on the wall, alternating bright and dark fringes. Okay? And that was the first really definitive experimental evidence that light could behave like a wave. Now, there is one technicality I will mention here about doing this experiment, and which is one of the reasons it was very difficult to do. the two little narrow slits in screen B, the slits labeled S1 and S2, they act as sources of light. And it must be the case that S1 and S2 act as what are called coherent sources of the light waves. What does that word coherent mean? It means the phase difference between the waves that are emanating from S1 and S2 must be always the same. Right? Whatever phase difference there is between the light waves emanating from 1 and 2, it has to stay that way. And that's why Young needed to start with the first slit A with the one narrow slit, so that then you had that single wave front in the middle region impinging on screen B. And then he found that S1 and S2 would act like what are called coherent sources. In lab, you don't need to have those two screens, A and B. You just need B with the two slits in it, because you're using a source of light that's already said to be coherent. You are using a laser, and the light that comes from a laser is automatically coherent in the way it's produced. All right, so what we want to be able to do is to quantitatively predict where those bright and dark fringes are going to be in this interference pattern. Okay? That's what we want to be able to do. We need to be quantitative, right? We need to use math. And so I want to talk about how we're going to find the location of the bright and dark fringes in this double slit experiment. Bright and dark fringes, again, over here on this viewing screen, C. All right, so now some more geometry. All right, we've got the viewing screen B, the screen B with the two narrow slits S1 and S2 that are acting like coherent sources of light. We've got the incident wave coming in. It's actually more curved if it came from the Young's situation. If it's coming straight from a laser, no, it doesn't have to be curved wavefronts. All right, then to the right of screen B is the viewing screen C. That's where we're looking for the interference patterns. And so we have picked a point, P, rather arbitrary, on the viewing screen. Okay? And we want to talk about whether point P is going to be a bright fringe, a dark fringe, or intermediate. All right, so let's be clear. We're taking that point P to be we've chosen an arbitrary location. We need a lot more geometry here. We will take a midpoint right between the slits S1 and S2, exactly in the middle, and we will extend that line straight across to the viewing screen, like so. Remember, the distance between the two slits themselves, I'll draw it over here, is little d. Then I'll draw the rays, R1 and R2, from S1 and from S2 to get to point P. And I will take a point at the midpoint between S1 and S2, and I will extend that in a straight line to point P. And the angle that makes, that line with the horizontal, is called theta. So there's a good bit of geometry there. Okay? We're going to need that little d and that angle theta, and this other distance y, which is the distance from point P to that central line between the slits that's been extended over to the viewing screen. Now here's one other thing that this picture does not get right. There's another distance, big D, which is just the horizontal distance from the screen B to the viewing screen C. You measured that with the big long tape measure. And we are always going to do this experiment so that the distance big D is much larger than the distance little d between the two slits. Okay? So we are always going to be assuming that big D is much, much larger than little d. This drawing doesn't really show that. So it's not quite realistic in that sense. The picture on the right, however, is a little more realistic, at least for what we're imagining. We are assuming that big D is so much larger than little d that those two rays that I drew in red and labeled R1 and R2 are actually, and they're both going to the same point P on the viewing screen, are actually, to a very good approximation, parallel to each other. So the picture on the left shows a kind of a zoomed-in view of the two slits, S1 and S2, and the rays, R1 and R2, that go from the slits to point P. We are drawing them as if they were basically parallel. All right, so here's the first big question. Why do we see interference on the viewing screen at all? Okay, why do we see alternating bright, dark fringes on the viewing screen? It's because the two slits act as two coherent sources. So I have two light waves, and there can be a phase difference between the light waves merely because the waves that travel from S1 and S2 to get to the point P can travel different distances. The waves travel different distances to get to the point P. And that's true no matter where point P is, except if point P is right at the midpoint there. Then the two waves do not travel different distances to get to P. But we're talking about the point P up above there. And so the wave that travels along R1 travels farther to get to point P than the wave that travels along R2. And what we want to know is the path length difference for the two waves, because that's what's going to produce the phase difference. And now I'm going to draw that path length difference in this picture, because what we've done in our exploded view of S1 and S2 is we've denoted the distance, little d, just between the slits, and then we've also dropped a perpendicular from S2 to R1, like so. And this angle theta is the same as this angle theta, here, here, and the theta over here. And this part of ray 1 and this part of ray 2 are equidistant to get to point P. So the extra distance that ray 1 travels is that part right down there. Let me now shade that in light green right there. That's the extra distance that ray 1 travels. That's what your book calls delta L, the path length difference. And all you have to do is look at this right triangle right here to see that delta L is equal to little d times sine of theta. Because in that right triangle, little d is the hypotenuse, theta is the angle up at the top, so that length that I shaded in green, the delta L, is d sine theta. Okay? All right. Now, let's look at a couple of cases. Suppose you're at point P, and the delta L, the path length difference, is an integer multiple of the wavelength of the light. 0 times lambda, 1 times lambda, 2 times lambda, 3 times lambda, etc. Then it turns out the phase difference phi between the two light waves at point P in radians will be 0 if delta L is 0, 2 pi radians if delta L is lambda, 4 pi radians if delta L is 2 lambda, etc. And then the two waves will be lined up crest to crest, and you'll get fully constructive interference at point P. Another extreme. What if the path length difference delta L between the waves is 1/2 of a wavelength? Then you will find that the phase difference phi between the waves in radians is pi radians, and they'll be lined up crest to trough. Or what if delta L is 3/2 of lambda? Then the phase difference will be 3 lambda. Or what if the delta L is 5/2 lambda? Then the phase difference phi will be 5 pi. ... Well, then the waves will destructively interfere. It'll be dark at point P, fully destructive interference. And there is, in fact, a useful, very useful, general relationship between the path length difference delta L of the waves and the phase difference phi in radians. And it's right here. The phase difference phi in radians is equal to 2 pi over the wavelength of the waves times the path length difference, delta L. Whereas we just said the path length difference for this classic double slit experiment is little d sine theta. So now let me do this. Let me take that result for delta L and let me substitute it into the formula for the phase difference phi and see what happens. Okay, so I'll do that over here to the side. Phi equals 2 pi delta L little d sine theta over the wavelength lambda. That's a handy result for this classic double slit experiment. And then let's look at the case of fully constructive and fully destructive interference. If we want to have constructive interference in a bright fringe at point P, then we want this phase difference phi to be either 0, 2 pi radians, 4 pi radians, 6 pi radians. The way to write that in general is 2m pi in radians, where m stands for an integer that can have the value 0, 1, 2, 3, ... And that will mean you'll have fully constructive interference and a bright fringe. And actually you can cancel the pi's on each side and the 2's on each side, and then you can rearrange that formula and express it like this. D sine theta must equal m times lambda. Let me bring that so that's more in view. And you have this cute little formula for locating a bright fringe. Little d sine theta must be an integer times the wavelength. If that's true at point P, it'll be at the center of a bright fringe. All right, now let's look at the other extreme, a dark fringe. Let me get my expression back here the way I want it. Okay, this is the phase difference phi between the waves at point P. Now let's say I want a destructive, fully destructive interference at point P, a dark fringe. Well, then we said that phi had to be pi, 3 pi, 5 pi, 7 pi, 9 pi radians, an odd integer multiple of pi. How can we express that? You can write it like this. 2m plus 1 times pi, where m can be 0, 1, 2, 3, ... You see how that can work? Plug m into that expression, m equals 0 into that expression up above, and you get pi. Plug in m equals 1, you get 3 pi. Plug in m equals 2, you get 5 pi, etc. Now I can cancel the pi. I can divide both sides by 2, just have to do the algebra carefully. That becomes a 1/2 right there. And then I can rearrange for d sine theta, and I get d sine theta equals m plus 1/2 times the wavelength. And that's the cute little expression for locating the center of a dark fringe. If point P is at a location where d sine theta equals m plus 1/2 times lambda, where m can be 0, 1, 2, ... then you know you're at the center of a dark fringe. Okay? All right, now that is basically using the angle theta to locate a bright fringe or a dark fringe. Remember what the angle theta is. Look up at the geometry. Take the horizontal line from the center of the slit straight across to the viewing screen. Then take the line from the center of the slits up to point P. And theta is the angle between those two lines. So that can be a way to locate a point P on the screen. Tell me what theta it is. But another way to locate point P is to tell me its y value. How far up or down along the screen is point P from the central point? And for that, I just need one more little bit of trig. Okay? Namely, let me just look at that picture. Tan theta is opposite over adjacent. Y over big D. Tan theta is y over big D. All right, so now I'm going to use that. So as I said, those expressions right up above give the angular location theta for a bright or a dark fringe on the viewing screen. But what are the corresponding y values for the bright and dark fringes? You just use, like I said, y equals big D tangent of theta. So if you want to know the y value for a bright fringe, you'll use big D tan theta, but you'll get your theta from the expression for a bright fringe. Little d sine theta equals m times lambda. So theta is the inverse sine of m times lambda over little d. If you want to know where a dark fringe, a y value for a dark fringe, again you use big D tan theta, but now you use little d sine theta equals m plus a half times lambda. Or theta is the inverse sine of m plus a half lambda all over little d. And this is how you can locate bright and dark fringes. Okay? Okay, and we'll be practicing with that in class. And you're using that in lab too. Now, there's one other idea in this lecture that I want to talk about. One of the useful quantities when you are studying waves is what's called their intensity. And intensity, by definition, is the time average power per unit area. Power per unit area. And so for this experiment, the classic double slit experiment, we could pick any point on the screen and we could ask, what's the power per unit area of the light there? That would be the intensity. And we actually want to be able to calculate that. We want to be able to pick a point P on that screen, tell you where it is, and then have you calculate the intensity in the interference pattern there. All right, so here's some things we need to know. On its own, the wave from either slit by itself, one slit only, has some intensity we're going to call I0. That doesn't mean initial intensity, it just means the intensity of the light going through a single slit. All right, now I'm just going to state the result because it takes a little bit of work to show it. You have to use the calculation method, uses a technique known as phasors. Yes, I said the word phasor. Okay, but I'm just going to tell you the result. So we've picked a point P on the viewing screen. What's the intensity there? I at point P. It's given by this formula. 4 times I0, the intensity from a single slit. Yes, 4, not 2. You might think, well, I've got 2 slits, so the intensity on the viewing screen will be 2 times I0. No, 4 times I0 times the cosine squared of phi over 2. Phi, remember, is the phase difference between the two waves as they arrive at point P. And remember how we calculate that phase difference. It's 2 pi over the wavelength times the path length difference. And the path length difference is little d sine theta. So that expression is this. 2 pi over lambda times little d sine theta. And so if you put that in for the phi, note that's phi over 2, you get this result for the intensity of the light at point P. And we will use that. 4 times I0, 4 times the intensity from one slit, times cosine squared of pi, little d, the sine of the angle theta at point P over the wavelength. Note, to use this result correctly, your calculator must be in radian mode. Okay? When you do that cosine squared, the calculator must be in radian mode. All right, now we have a couple of pictures to talk about. First on the left. Well, that's a representation, a photograph, of a two-slit, double-slit interference pattern, which would be similar to one of the patterns you saw on the wall if you've done part B in lab in the last experiment. And you see alternating bright and dark fringes. Bright, dark, bright, dark, bright, dark. Now, the pattern kind of goes horizontally in this image, so there's a little bit of a subtlety here that can be confusing. This image was made with the two slits in the screen parallel to each other and being vertical, not horizontal, not like this, like this. And that's the way you've done the experiment. Your slits were vertical. Okay? Whereas the pictures we've been drawing show the slits being horizontal. Okay? And so then the interference pattern goes up and down. Okay? And I'll show you an animation. But I want to also show you the graph on the right. We have here a plot of the intensity, I, at point P on the screen as a function of the phase difference phi at point P on the screen. Imagine point P moving from the central point up or down. So if phi is 0, for example, phase difference is 0, then the path length difference is 0. The point P must be right at that midpoint. And we have a maximum, a bright fringe, and we get the maximum intensity there. 4 I0, 4 times the intensity from one slit. If I go farther out to the next peak to the right, where I get the maximum intensity of 4 I0, that corresponds to a phase difference phi of 2 pi radians. And whereas the central maximum corresponds to m equals 0, this next maximum corresponds to m equals 1 and to a path length delta L of 1 wavelength. The next peak, again at intensity 4 I0, is with a phase difference of 4 pi, m equals 2, and a path length difference of 2 lambda. And it repeats. Now, here we have a minimum intensity, right? The intensity is 0. That's the first such minimum. And that corresponds to a phase difference phi of pi radians. It's m equals 0 for the minima, and it's a path length difference of a half a wavelength. The next dark fringe right here, again, has an intensity of 0, corresponds to a phase difference phi of 3 pi radians. The m is 1 for the minima, and the path length difference is 1.5 wavelengths, and so forth. Okay? So the intensity smoothly varies from maxima intensity, 4 I0, to minimum, 0, and back and forth. Okay? All right. Let me show you then now some Wiley Plus animations to try to help you visualize what we're talking about. So here's another representation of the classic double slit experiment. And the screen with the slits is drawn in brown. And the slits are drawn being somewhat long, rather narrow, and having a distance little d between them. And they're horizontal, just like the book is assuming. And then it shows in a schematic representation the diffracted waves that have come from the incident waves coming in. And then you see on the viewing screen the bright fringes. See where it's bright? M equals 0, M equals 1, M equals 1 are going up and down, vertical. And we have alternating, bright, dark, bright, dark. I can, in this animation, also change the distance little d between the slits. I can bring them closer together or farther apart. Let's see what happens to the interference pattern, specifically the spacing between the bright fringes. Let's make the spacing little d between the slits, it's right now twice the wavelength of the light, let's make it bigger. Okay, I'm going to drag that slider and make little d bigger. Let's see what happens to the interference pattern on the viewing screen. If I can get it, there we go. There's a bit of a lag here because it has to redraw the image, so that's not very helpful, is it? Okay, boy, I don't know why it's so sluggish. Okay, but I think you can see that as I made little d bigger, I made the slits farther apart, maybe somewhat, perhaps counterintuitively, but the interference pattern gets more closely spaced, scrunched together. The fringes get closer to each other. And if I try to go the other way, I don't think it's going to work very well. Make little d smaller, put the slits closer together, the interference pattern actually spreads out. Okay? All right, now, let me show you another picture. Sorry, let me get this where I want it. Okay, this is another representation of the two slits. The viewing screen is on the left. Excuse me, the first screen is on the left. Those two dots represent the slits. You can see an expanded view of it. The viewing screen's on the right, a distance big D away from the first screen. And right now our observation point is right on the central axis, where we would have an intensity maximum. And those two arrows on the right represent, in essence, the electric field vectors for the waves from the two slits together. And they're lined up, and so you add them to get the net, and you get a large value, and that's why you have a maximum. This is this phasor business I was talking about. Now I'm going to move the detector up on the viewing screen. And as I do, the phase difference between the two waves gets bigger. The corresponding electric field vectors are no longer in phase with each other. And if I get them so that they're exactly pi radians out of phase, then they exactly cancel. And right now my point, P, is at a point of fully destructive interference. But if I keep going upward, then the phasors rotate again, and I'm getting to maximum again, fully constructive interference, bright fringe. Keep going. This represents the phase difference between the two waves. Boom, nothing again, fully destructive. And it just keeps repeating. Fully constructive, fully destructive, fully constructive, etc. So you can kind of see a little bit of what's happening there. Let me show you another one. Now we've got slightly different lighting effect here to help you see intensity and how you have bright and dark fringes. Sorry, so the fringes are over there on the right on the viewing screen. We're assuming red light. Okay, and again I can move the detector. Right now I'm at the central maximum at the middle, so the intensity is at maximum. And I is 4I0 as the graph shows. And I start moving my detector upward. And when I get to the center of a dark fringe, my waves are exactly out of phase, and my dot on the intensity graph is down at the bottom at a minimum. If I keep going upward, if I'm at the center of the next bright fringe, my waves are in phase. I have a maximum intensity. My dot on the graph is up at 4I naught. I go up some more. At the center of the next dark fringe, my waves are exactly out of phase. I have no intensity, and it just keeps repeating. That's the pattern we want to be able to study and understand. Okay? All right, so I'm going to end the video with just a little bit of practice. It's not actually for class engagement. We're going to do it together. I want us to do some practice calculating the intensity, let me get that back in view, of a double slit interference pattern. Because that formula for the intensity takes a little bit of practice to get used to. So, using the double slit experiment geometry, we've got the figure reproduced below, we are to calculate the intensity at the point P on the viewing screen, given the following values. Ready? The distance y of point P from the central axis, 20 centimeters. The distance big D between the first screen and the viewing screen, 1.25 meters. The distance little d between the two slits, 0.1 millimeters. So the figure over there is not even close to being to scale. The wavelength lambda of the light coming in, 546 nanometers. The intensity of light from a single slit, I0, 4 milliwatt per meter squared. We are to give the answer for the intensity at point P in milliwatt per meter squared, showing our work. And then we will have to identify what kind of interference we get. Okay, so let's write down the formula for the intensity we will observe at the point P. Just going to use the formula I showed you. 4 times the intensity from a single slit, cosine squared of pi little d sine theta over lambda. And we have to figure out the right values to put in. A lot of these values were given. We're given I0 directly. We're given little d directly. We're given lambda directly. The only thing we really have to work at is finding the correct value for the angle theta. Theta is the angle between that central horizontal line there and that line to point P there. That's theta. That's what I have to find. Well, I think the figure makes it pretty clear that tan theta is y over little d. And I'm given y and little d, so I can find theta. It's the inverse tangent of y over little d. Let's plug in the numbers and see what we get for theta. Inverse tangent of y, 20 centimeters, well, 0.200 meters, and big D, 1.25 meters. The meter cancel. Calculator in radian mode, and take the inverse tangent. I'll keep extra sig figs. 0.1587, and let's write radian. Okay, we have found the angle theta between the horizontal line across the center and the line to point P. Now we can use the intensity formula. I'm going to show all the numbers. IP equals 4I0, 4 milliwatt per meter squared, times cosine squared of pi little d, now put in consistent units, 0.1 millimeters is 0.1 times 10 to the minus 3 meters times sine of the theta we just found, 0.1587 radians. Again, make sure your calculator's in radian mode, over lambda, the wavelength, 546 nanometers. 546 times 10 to the negative 9 meters. Note the unit of meter here cancels here. Again, make sure your calculator is in radian mode. I would put all these numbers in my calculator. I would then take the cosine of it, and then I would square it. And then I would multiply by 16, yes? And I'll get the intensity in milliwatt per meter squared. 15.4 milliwatt per meter squared. That's the intensity at the point P that they're talking about. Now what they want us to do in part B is figure out whether this is fully constructive interference, fully destructive interference, or intermediate and closer to fully constructive, or intermediate and closer to fully destructive. I think the easiest way to do that is to take the ratio of the intensity we got at point P to the absolute largest intensity we can get, 4I0, right? And that occurs when we have fully constructive interference. So that ratio, you put in 15.4 over 4I0, which is 16, and you get 0.96. The closer that ratio is to an integer, the closer you are to fully constructive. 0.96 is very close to 1. So what we have here is intermediate, but closer to fully constructive. In fact, very close to fully constructive. If we didn't keep enough sig figs, we might be tempted to say fully constructive. But our sig figs tell us that it's not quite fully constructive. All right, so we're going to have to do more practicing, there's no doubt about it. So in Monday's class, we'll be practicing with studying the double slit interference geometry. And that's all for this video.